Hello, everyone. My name is Gunnar Eppin, and I'll be presenting on behalf of my collaborators our work, crowdsourcing a labeled dataset using binary choices versus probability judgments. We are interested in crowdsourcing a labeled dataset in the context of AI-assisted medical image diagnostics. The so-called medical AI information value chain has 4 stages. It begins with image annotation. Ideally, experts are doing the labeling, but oftentimes this is not time or cost effective. So as a result, data annotation companies typically will outsource image annotation to skilled non-experts. And once these skilled non-experts have provided several annotations for a bunch of images, these annotations are then collected in some intelligent manner or combined in some intelligent manner that we're going to say that forms for each image a crowdsourced label. For example, maybe you only want the annotations from the most accurate experts to go into the labeling process, or the most accurate annotators. The third step is then training the AI system on these crowdsourced label datasets. And finally, the AI system is deployed in a clinical setting to assist the human physician in making their diagnosis. AI is often pitched as trying to replace humans, or it maybe seem like that, but we just like to point out that the value chain both begins and ends with humans, beginning with human annotators and ending with human clinicians. Generally, my research group wants to know how can we best construct AI for medical image diagnostics? And our focus is on the data annotation component, because this will impact the entire chain. Any changes to the first step of the chain is going to have downstream effects through the others. And also the lack of labeled data sets is a major bottleneck for medical AI. Therefore, we ask, can ideas from cognitive psychology and experimental economics improve the data annotation process? The current approach is annotation. Like we said, this work is typically outsourced to skilled non-experts. The image on the right is actually a screenshot from a data annotation platform called Centaur Labs. On this platform, they will typically elicit classifications, or in this case, binary choices from their annotators. The binary choice is purely between deciding whether the thin lesion is a melanoma or a nevus. And after aggregating a bunch of, or after obtaining a bunch of annotations for a single image, these binary choices here are aggregated into a single label using wisdom of the crowd. Wisdom of the crowd is this phenomena where the sort of combined or aggregated classification from a group is typically more accurate than any or most of the individuals in the group. For example, here, if 3 people see this image, 2 of them say nevus, the majority of the crowd is saying nevus, and the label will then be a nevus. We are interested in how to improve this annotation process. So binary choices don't include sort of confidence or some sort of uncertainty, whereas if we were to instead elicit probability judgments rather than binary choices, that would permit participants to express some certainty, where a less confident classification would be closer to an intermediate probability or 50, and a more confident would be at the extremes. Binary choices throw this information away. For example, if in the previous example, the 2 people who said nevus would only say there's like 55 or 60% chance that the probability lesion is a nevus, whereas the person who said melanoma is very confident that it is not nevus. If you were to take the average of those probability judgments, that would be only 40% nevus, and therefore the crowdsourced label would be melanoma here. So the crowdsourced label will differ or can differ depending on whether we're eliciting binary choices or probability judgments from participants. Which brings me to our research questions. First, we want to know, how does annotation mode, that being either binary choices or probability judgments, impact the accuracy of the wisdom of the crowd labeling approaches? And second, we want to know, how does annotation mode impact the accuracy and calibration of models trained on the wisdom of the crowd labels? We care about calibration in addition to accuracy because, well, when a machine outputs, say, a likelihood of 30% cancerous, we're going to look at 100 instances where it said 30% cancerous. Ideally, 30 of those instances, the ground truth is indeed cancerous. So accuracy more pertains to the classification information, whereas the calibration refers to sort of the accuracy of the probabilistic information provided by the model. To address these questions, we designed a study that recreates the first two steps of the information value chain. So first, we collect annotations from non-experts, both binary choices and probability judgments. Second, we aggregate these annotations into crowdsourced labels using wisdom of the crowd. Third, we evaluate the accuracy of these crowdsourced labeled data sets. Fourth, we train machine learning models on these data sets. And finally, evaluate both the accuracy and calibration of the models. The images in our study are white blood cells. They're either blast cells, which are cancerous, or non-blast cells, which are non-cancerous. You can see a few example images on the side. We put multiple non-blasts up there to show that there's quite a good amount of variety in those images. Some do not look at all like blast cells, whereas some do, like the one on the right. And the blast cells are a bit more homogeneous. So some non-blasts are clearly non-blasts, whereas some non-blasts, the line is pretty blurry. This dataset originally came from Troop et al. 2018, where 3 Vanderbilt pathology faculty independently classified 840 images. Of these images, there were three-way agreement. That means each expert arrived at the same classification on 633 of them, and we used a subset of those images that were clear and only had one cell in the image, just to make it easier for the MTurk participants. And lastly, we take expert agreement to be ground truth for these image labels. For this study, we recruited 400 participants from MTurk. Half provided binary choice annotations, whereas the other half provided probability judgments. They were each paid $1 with potential for a $5 bonus. Before going and providing annotations, they were trained to classify, or trained to learn differences between them. First, they went through something called what we call an acquisition phase, where they just see several images from each class to help them familiarize similarities within the classes and also differences across classes. And second, they practice by classifying images as either blast or non-blast with the help of feedback. And this study was pre-registered. For the testing phase, where we're eliciting the annotations from participants, in the binary choice condition, we would merely ask people, do you think this is an image of a blast cell? Yes or no. This testing phase consists of 100 trials. There's no feedback, and one trial is randomly chosen for a $5 bonus. If they were correct on that trial, they got the bonus. If they were incorrect, did not get it. For probability judgments, very similar, except here we ask, what do you think is the probability that this is an image of a blast cell? Again, 100 trials with no feedback, one trial randomly chosen for the bonus, And we use proper scoring rules to determine the likelihood that participants would receive the bonus given their probability judgment and the class of the cell. And this was done to incentivize truthful reporting of probabilities. Which brings me to our label results. When first looking at the mean individual accuracy, so that is, we calculate the accuracy of each participant in each condition and then average across participants, you see that they're both right around 66% accurate. So at the, and note, for probability judgments, when we're computing accuracy, 50%, if it's over 50%, we took that to be blast classification, and below 50%, took that to be a non-blast classification. And that was for computing individual accuracy for the probability judgments. And we see that they're pretty much on average equivalent in terms of skill in the two conditions. Whereas when we look at the crowdsourced labels, so the crowdsourced labels in binary choice is just aggregate which one has more votes. And then probability judgment is take the mean. Again, it's over 50%. To take it as a blast, whereas below 50% take to be a non-blast. We see that the probability judgments lead to far more accurate crowdsourced labels at about 88% accuracy compared to binary choice at about 83% accuracy. For each image, we had between 14 and 64 annotations. And we were curious with if we had to collect fewer annotations, so weren't as much participants, how does the number of annotations impact accuracy? So what we would do is randomly select a subset of the annotations for an image, compute what the label would be, look at the accuracy, and then simulate that random subset selection process a bunch of times and see what the results are. And we could see that the accuracy for the probability judgments not only has a higher ceiling, but also grows much faster in terms of the number of annotations compared to binary choices. And therefore, we can say that to reach an arbitrary level of accuracy, fewer probability judgments are needed for annotation processing. With our labeled datasets, not the subset ones, the full ones, we train the convolutional neural network. We use 30 random testing/training splits where 80% of the images and labels for each split were used for training and the other 20% were used for evaluating the models. We found that, unsurprisingly, the model trained on the probability judgment dataset is much more accurate compared to the one on binary choices. I say not surprising since the labeled dataset is also more accurate. And when we're looking at in terms of calibration, the metric is expected calibration error, so lower is better. And so here, we see that the probability judgments are producing a lower calibration error, meaning we have a better calibrated model. To wrap everything up, I'd like to see if we've answered our research questions. The first one being, how does annotation mode impact the accuracy of the wisdom of the crowd labeling approaches? We find that probability judgments lead to more accurate labels, and also fewer probability judgments are required to reach an arbitrary level of accuracy. Next, we're curious, how does annotation mode impact the accuracy and calibration of models trained on the crowd labels? And we found that the models trained on labels obtained via probability judgments are more accurate and better calibrated than those obtained via binary choices. For a wrap-up presentation, just want to acknowledge the team. It's them. None of this presentation would be possible, so just thank you to all of you. And with that, I will conclude the presentation. Thank you for listening, and please feel free to reach out to me if you have any questions.